Hi, everybody, and thank you for joining us today for our webinar, Understanding How Hydrophobic Insulation Impacts CUI. My name is Kim Melton, and I will be your moderator for today's presentation. Before we dive into introductions, I do want to go over a few logistics. First and foremost is that we're having some extreme weather here in Denver today with blizzards and power outages in the area. So if we do experience a power outage, we're going to be rescheduling the webinar for a later date. On a more practical note, if you have any questions or concerns throughout the webinar, you can submit them to our panel during the presentation at any point via the Q&A feature, and we'll address your questions live at the end of the presentation. Now, if you don't see the Q&A to the right side of your screen, look for a series of circular icons at the bottom middle part of your screen, and you can select the icon with the ellipsis in it, and that's going to open up a menu with an option for Q&A at the top. If you select that option, it'll open a dialog box that you can use to submit questions, and that's going to open to the right side of your screen. Now, additionally, we'll follow today's webinar with a survey, and this is your opportunity to provide us with feedback on how we did today, ask any additional questions you may have about the topic on the webinar, or even suggest new topics for webinars you'd like to hear in the future. And we're continuously striving to improve and evolve our webinars, so if you have any comments or suggestions as to how we can better accomplish this, or even if you feel like we've missed the mark today, we'd encourage you to fill out the survey. We use your feedback to improve our webinars and provide the information that has the most value to you. Now, this survey is also part of how we deliver the JM experience, and the JM experience is based on 4 pillars of the JM culture, and that's people, passion, perform, and protect. And we believe it's critical to make sure that we hear, understand, and respond to your needs in order to deliver the best interaction to you. So we offer webinars like this one to help educate the market and offer a tool and a resource for you and your business. But this isn't just a one-way street. Your feedback is really a key component to that, and it's crucial to helping us evolve to better meet your needs. We're frequently asked whether or not we send out these presentations upon their conclusion, and we don't actually send out the presentation itself, but we do post a recording of it online for you to watch at your leisure or even share with your colleagues. And this ensures that you can have the presentation within its full context and refer back to it as a resource if you need be. Now, when this is live online, we'll send you an email with a link to it so that you can access it easily. So with that, let's dive into introductions. Joining me today are Marybeth Jones and Matt Ball, who are going to kick us off.
Hi, my name is Marybeth Jones. I've been with JM for 7 years. My background is in chemical engineering. I have spent time as an engineer in both refining and manufacturing, and I'm currently supporting our industrial installation for rigid products doing product development.
Hello, I'm Matt Ball. I'm the regional sales manager for the Gulf States for Johns Manville's Industrial Group. I've been with JM for 12 years, based in the Houston, Texas area, and have had industrial insulation responsibilities for Texas, Louisiana, Arkansas, and Oklahoma for the past 2.5 years. Prior to that, I spent 9.5 years as market development manager for JM's HVAC and mechanical fiberglass installations group. Thank you again for joining us to learn more about hydrophobicity and how it relates to insulations and corrosion. Let's take a look at some of the items we'll be discussing in today's presentation. We recognize the growing influence of hydrophobicity in regards to insulation, so we'd like to define the differences between hydrophobicity, water resistance, and water repellency. We will review how insulations are tested for water repellency and which ones offer a level of water resistance. We'll also spend some time on corrosion inhibitors like the XOX, and how they can influence combating CUI versus hydrophobic treatments alone. So, hydrophobicity has had an impact on insulation choices recently, as we've noticed an increase in demand for insulations that resist water. So what is all the hype about hydrophobicity? Much of it has to do with being part of a CUI strategy. So let's take a look. The financial impact of CUI is tremendous. 6 years ago, NACE International, the National Association of Corrosion Engineers, estimated that the effects of CUI had a global impact of $2.5 trillion. CUI is one of the most costly spends for maintenance in the oil and gas and petrochemical industries. CUI is difficult to detect as it remains unseen and hidden under insulation systems until some type of inspection is conducted. CUI can also be a large contributor to piping failures and downtime in facilities, which can have a costly financial impact as well. Employing sound and effective strategies to mitigate CUI can have a positive impact on capital spend for maintenance. Choosing the right insulation can be a significant part of a CUI strategy, and investment in the proper insulations can realize a substantial return on the investment. So, to develop strategies for CUI, we need to take a look at how corrosion happens in the first place. So what are the conditions needed for corrosion? Well, there are generally a few ingredients and conditions needed for corrosion to happen. There are liquid water and or corrosive chemicals, as well as contaminants in the liquid water that contribute to the corrosion, oxygen, and an acidic pH level of less than 7. Temperature is also a component between 100 and 300 degrees F. When these things come together, you can have corrosion develop. There are design considerations to limit the exposure to these ingredients, which are part of an overall CUI mitigation strategy. If we can control these factors, we have a better chance of limiting the CUI risk. Exposure to oxygen is very difficult to control since it's around us all the time anyway, but there are measures that can be taken to limit the other factors. For instance, without exposure to liquid water or corrosive chemical compounds, the CUI risk can be lessened. Also, controlling pH levels that the piping is exposed to can have an impact on CUI too. The type of corrosion and rates of corrosion can also be impacted by the environmental exposures to the piping, as well as the properties of the insulations being used. Wet climates can have a greater impact on corrosion than dry climates if the piping system is not protected and the insulation system is not protected. Keeping water off the piping is one step that you can use to combat CUI. As you can see on the right, this metal jacketing has been damaged, which could potentially allow a path for outside water to enter the insulation system and possibly reach the piping surface. This could have a profound impact on the piping as it relates to CUI. Here is a corrosion band chart. The service temperature also has a large impact on CUI rates. The corrosion temperature bandwidth is depicted in this slide, and as you see, all types of insulations here that are used in the industrial insulation industry fall within service temperatures in this bandwidth. Johns Manville manufactures the top 5 insulations in this illustration, and cyclic temperatures in this bandwidth can pose a higher risk to CUI. In systems that have cycling temperatures or periodic shutdowns, there are many real-world situations with exposures to these temperatures in the corrosion band depicted here. So how does CUI occur? Here we'd like to illustrate how it actually happens. So let's think of a 9-volt battery. Things are pretty stable there until a conductor between the 2 poles on the battery is introduced. Once that happens, there's an electrical flow. The small spheres on the bottom of this illustration depict molecules of a steel surface. In the case of corrosion, when water is introduced, the conductor would be the acidic electrolytes in the water, which would bridge the gap between the anode and the cathode, resulting in iron oxide, or also known as rust. There's no actual loss of mass, but there is a change in some of the steel molecules to iron oxide and the displacement. When this occurs, corrosion pitting can happen, which diminishes the localized thickness of the steel, and in turn could result in a weak point in the piping surface or thickness. So defining the terms, we'd like to define some of the terms being used now, and with that I'll hand it over to Marybeth.
Thanks, Matt. So what is hydrophobicity really? There's a lot of terminology out in the marketplace that refers to hydrophobicity. In this part of the presentation, we're going to explore what those terms are and what they really mean. So, hydrophobic and hydrophilic, not words that one regularly uses in everyday speech. I'm not at the store trying to decide what paper towels to buy thinking which of these is most hydrophilic. So how did we get here? Personally, I blame somebody in marketing. Nonetheless, these are the terms that are getting used regularly when referring to the physical properties of insulation systems. Hydro comes from the Greek word for water, phobic, lacking affinity for, philic, having affinity for. These two terms are complete opposites and both extremes of the spectrum. So what are the terms that exist in the gray areas between? Have you ever bought a jacket thinking that it would keep you dry in the rain, or in my case today, a blizzard, only to find out the hard way that it doesn't? If you have, then you have personally experienced the gray area between hydrophobic and hydrophilic. Hydrophobic really, in a technical sense, as it states here, refers to molecules and surfaces or components, not composites or systems as you would see in an insulation system. So water resistant is really the lowest level of hydrophobicity. Depending on the raw materials, this may be an inherent property or something that required an additive or a surface treatment to achieve. It will shed bulk water, but becomes saturated readily. Water repellent is kind of the grayest of the gray areas. Materials that live in this part of the spectrum are likely to have some raw materials that have inherent water repellency, but will also likely have an additive. It will also shed bulk water, like the water-resistant material, but in time become saturated. The degree of both water shedding and time to saturation will vary greatly depending on the base material and the amount of additive. Waterproof, the bottom line is that a waterproof material will not become saturated no matter the duration of water exposure. It's likely to have a significant amount of additive throughout the material or be made up entirely of materials that are intrinsically hydrophobic. So what are those materials? Hydrophobic additives generally fall into one of these four categories. As you can see, they vary based on chemistry, cost, temperature stability, and each has advantages and disadvantages depending on the application. The big thing that you'll notice, though, is that as you increase in cost, you increase in thermal stability. What that temperature limit means is that above those temperatures, the additive will start to degrade, and given enough time at or above those temperatures, you will lose the effect of the additive altogether. But not all applications require high temperature limitations, and as Matt has pointed out, that the main CUI range is between 100 and 350 degrees. So combinations of these additives can give an optimal performance at an optimal cost. So let's move on to how these additives can be implemented. Additives applied as a surface treatment are typically designed for water-resistant applications. They can be applied to a finished product or to a fabricated product. Surface treatments usually penetrate between a 1/16 and an eighth of an inch into the surface of the material. Limitations of this type of application is that any damage to the surface of the material will result in a compromised area where you can have severe saturation. Typical applications for this method are via an air pressurized spray, similar to paint application, or a dip or curtain coat application. So additives incorporated into the base formula of the material can result in a finished product that is water resistant all the way up to waterproof. Where it ends up on that spectrum will depend on the additive, the amount used, and the inherent properties of the base material. Our Thermo 1200 uses a small amount of additive, but the physical properties of calcium silicate are hydrophobic by nature, so it ends up as a water-resistant material. Whereas the Sproul 1200 also uses a small amount of additive, but the expanded perlite is inherently hydrophobic, so the result is more of a waterproof material. However, since both of these materials utilize an additive, given enough time at a high enough temperature, thermal degradation will result in decreased or negligible performance. Then there are materials that are just inherently hydrophobic. It's not only a part of their chemistry, but it's also in their application and their structure. In these cases, there is no way to remove the water repellency trait from the physical properties of the material. Unlike the additives, the water repellencies of these materials will not thermally degrade over time. However, they may have other inherent limitations depending on their raw material properties. So now that we've covered the varying ranges of water repellency and how that water repellency is achieved, how do we measure it? So there are two major bodies that govern testing and material standards internationally. They are ASTM, the American Society for Testing Materials, utilized mostly in the US and Canada, and then there's the British Standard European, which is used throughout Europe. For water repellency testing, both of these bodies have test methods for measuring water repellency, but test methods don't contain limitations. So any pass-fail requirements, if they exist, would be in the material specification. That's important to remember, the distinction that the test method is only a directive on how to run or execute the test. They can be used to compare materials, but any limitations, if they exist, would be in the material standards themselves. So these tests generally fall into three categories. Full immersion, which is where the material is forcibly submerged in water to determine absorption. Partial immersion, which is where the material is just placed in standing water to determine absorption. And then water vapor sorption, where the material is just exposed to a humid environment, but no actual liquid water. These test methods are designed for a specific end-use application, but only so many test methods exist, and it's common to use an existing accepted method rather than to try and develop and gain acceptance for a new test method, even if it doesn't exactly fit the end-use application. So something to be cognizant of when comparing materials is making sure that the test method used is reasonable for the end-use application. For example, the test method that JM developed for the calcium silicate water resistance is an internal test method based on the end-use application of being able to withstand a rainstorm for 20 minutes. No standard test method exists for that application, so a test method was developed. So let's take a closer look at the test methods that we have listed here. So the ASTM C411 water vapor testing. This test method for water vapor sorption requires that the material be conditioned for 2 hours to remove any inherent moisture and then weighed, subjected to a high humidity environment for 96 hours, and then reweighed. This test method is required in the ASTM material specifications for mineral wool, both industrial and commercial applications, as well as the ASTM material specifications for aerogel. The BSEN 1609 and 13472, these water wicking or partial submersion tests really aren't vastly different. The flat material or the pipe are weighed, then subjected to standing water for 24 hours, allowed to drain, and then reweighed. Unlike the vapor exposure tests, these partial submersion tests don't require a preconditioning to remove all internal moisture. They're just conditioned at standard conditions prior to testing. And that's because the expectation is that the inherent moisture in the product will be negligible compared to the liquid water absorption. Since this test method isn't a part of any ASTM material specification, there are no limitations on acceptable absorption. JM targets a weight gain of less than 1 kilogram per meter squared. The reporting units on that are metric because it's a European standard, but it equates to about 0.2 pounds per foot squared. So finally, the submersion testing, the ASTM C1511 and C1763. In both of these test methods, the material is weighed, subjected to a forced submersion for a duration, then drained and reweighed. The ASTM 1763 is actually a prime example of a test method that is used for multiple different applications outside of its natural scope. The perlite specification, material specification, ASTM 610, actually requires a C1763 submersion test. However, the material specification states that the samples must be preheated to 600 degrees for 4 to 4.5 hours prior to testing, and that the immersion time is actually 48 hours as opposed to the 2 hours stated in the test method. The aerogel specification, material specification, ASTM C1728, also requires a 1763 test for type 3, which is their high temperature application materials. In that specification, the samples are submerged for 2 hours per the standard test method, but only after preheating the sample for 24 hours at 600 degrees and allowing it to cool back to room temperature. So another reason to really understand not only the test method, but the material specification as it applies the test methods. If the perlite and aerogel were tested direct to the C1763, they would likely have no weight gain, but given the provisions in the material specifications, they do. And even though both specifications require the same test, it is applied so differently that the results aren't even comparable. So now I'll hand it back over to Matt to take a look at the insulations.
So let's look at some insulations that inhibit water ingress. When it comes to selecting water-resistant materials, there are a multitude of options, as you can see here. JM's the only manufacturer to offer multiple types of water-resistant insulation, and our complete water-resistant insulation portfolio is shown on the left, with Manville 1200 pipe, Thermo 1200 calcium silicate, Insulthin HT, which is thin hydrophobic blanket, and Sproul 1200 perlite. What you see on the right of the screen are two other materials that we do not manufacture but fall into a water repellent category, silica aerogel and cellular glass. As Marybeth said earlier, the level of resistance in each of these insulations varies. For example, Thermo 1200 calcium silicate is designed to shed bulk water like what you would see in an afternoon rainstorm, in comparison to Sproul 1200 and Insulthin HT, which are designed to be non-wicking. If you're familiar with any of these insulations, you'll know that beyond water repellency, their features vary substantially. Insulthin HT is very thin. It's dramatically thinner than any of its other counterparts. Manville 1200 pipe is very lightweight, and Sproul 1200 and Thermo 1200 do offer superior compressive strength, as well as having the XOX corrosion inhibitor. This allows specifiers to select physical differences that their application needs without sacrificing water repellency. With that said, when it comes to preventing corrosion, system designers should not rely solely on hydrophobicity to inhibit CUI. Next, Marybeth's going to compare the efficacy of corrosion inhibitors to hydrophobicity and establish which has a stronger influence over an insulation's corrosion potential. So another thing to consider for strategies in CUI is utilizing insulations that have integral corrosion inhibitors. Keep in mind, corrosion inhibitors are not the same as hydrophobic substances, and I'll let Marybeth elaborate more on it.
Thanks, Matt. So far, we've talked a lot about water as it relates to the insulation's physical properties. But what does that really mean when it comes to CUI? We know that water is an integral part of the corrosion triangle, but is it really the most important piece? And how does that compare to the material properties, including corrosion inhibitors, when it comes to CUI? So both the corrosion inhibitor and hydrophobic treatments can be integral to the product. But unlike a hydrophobic treatment, the corrosion inhibitor will not degrade over time and is present for the life cycle of the material and installation. The corrosion inhibitor may not prevent water ingress into the system, but it's not intended to. The XOX corrosion inhibitor is designed to protect the piping once the system inevitably becomes compromised and the water is already present. So this works utilizing two mechanisms to prevent corrosion. The first mechanism that our corrosion inhibiting package uses to combat corrosion is through pH buffering. Low pH compounds from the environment can accelerate corrosion on the pipe surface, especially at high temperatures. When the XOX corrosion inhibiting compounds in the insulation come into contact with water, they will result in a slightly alkaline environment. Those alkaline components in the system will neutralize any acidic compounds that may enter the system to keep the pH above 7. In our third-party accelerated corrosion testing, we found that after 6 months of testing, the pH of the insulation next to the pipe surface was approximately 10 for both the Thermo 1200 and the calcium silicate and Sproul WR 1200 perlite, indicating that it will maintain the pH buffering capacity under severe conditions for the life of the material. The second mechanism that we will discuss is the formation of a silica-based surface coating. This occurs when the water makes its way through the insulation and pulls with it the silicate anions in the insulation, leaving them on the pipe surface. And this creates a silica gel-based coating on the surface of the pipe. Over time, those silicate anions on the pipe surface can also react with the iron compounds on the pipe surface to create an iron silicate coating. And you can see both of those mechanisms of formation on the bottom of the slide. Both of these coatings protect the pipes simply by creating an inert barrier to corrosive materials. And again, both of these mechanisms require water to be present in the system. We designed for it not to be there, but in the event that it's there, this is how the water-activated corrosion-inhibiting properties of the insulation will work to protect the piping. One test protocol that we use and is pretty standard throughout the industry to evaluate corrosion on a laboratory scale is ASTM C1617. This protocol uses a liquid extraction on the insulation to remove any leachable compounds. That leachate is then exposed to heated carbon steel coupons repeatedly over the span of 96 hours. And it's dripped onto the heated coupons in a way that the water is boiled off readily and there's no pooling or standing water at the surface, but there can be some variance in this just based on the person setting up the test equipment. So after the 96-hour test, the coupons are then cleaned of any corrosion products and then reweighed. The weight loss is then used to calculate a mass loss corrosion rate, or MLCR, in mils per year. In addition to the insulations, 3 reference samples are also tested at the same time, and they're deionized water, 1 ppm and 5 ppm chloride solutions. So it gives you a good reference for the relative corrosivity of the insulations to those standards. So as you can see in the table, the Thermo 1200 calcium silicate and Sproul WR 1200 perlite products have corrosion rates that are less than deionized water. The corrosion inhibitor both buffers potential corrosive ions and forms the silica gel layer to protect the metal surface, which results in the lower corrosion rate than DI water. The silica aerogel blanket and water-repellent mineral wool, on the other hand, have a MLCR that is higher than DI water and much higher than the Thermo 1200 or Sproul WR 1200. So both the aerogel and mineral wool have low or negligible water absorption, but the material properties, once exposed to water, still results in a higher corrosion rate. One of the questions that comes up pretty often from end users is the longevity of the corrosion inhibiting package and if it ever runs out. We decided to test this on the Thermo 1200. Based on the chemistry of the Thermo 1200, we know the inherent composition of the calcium silicate material along with the mechanism of silicate release should not lead to a reduction in corrosion inhibition properties over time. In this test, we subjected the Thermo 1200 to repeated wet-dry cycles and then used one of the test methods from ASTM 871 to measure the leachable silicate content of the Thermo 1200 over time. What we found was that after 40 cycles, we did not see an appreciable drop in silicate content. Therefore, we anticipate no impact to the inhibition performance over time. In our accelerated corrosion testing that we've had performed by a third party, we found that there are 2 types of corrosion that can occur under extreme real-world conditions. They are the formation of magnetite and hematite. Hematite, or rust, in the picture on the left is reddish-brown, flaky, and pretty easy to remove from the base surface. Magnetite, in the picture on the right, is a more stable corrosion layer that can actually impede further corrosion. The XOX corrosion inhibitor in our Thermo 1200 and Sproul WR 1200 creates the environment that drives the formation of magnetite over hematite, even though both of those materials have varying degrees of water repellency. The tested silica aerogel blanket, although listed as a hydrophobic material, doesn't contain corrosion-inhibiting chemistry, resulting in an environment more prone to hematite formation and a greater potential for corrosion. So, water intrusion into any insulation system is inevitable. We design systems to be as robust as possible, but every system has the potential for failure. Jacketing gets damaged, hydrophobic treatments degrade over time, and water will end up present at the pipe surface. When that happens, the chemistry of the insulation material is what really drives the potential for corrosion. When it comes to CUI prevention, the insulation material itself has more influence over corrosion potential than the hydrophobicity.
Well, let's take a look at other things to consider when specifying insulations and how hydrophobicity should be factored into that decision. Hydrophobicity alone is not the cure-all to CUI, especially in cyclic high temperature situations. That's where hydrophobicity is less effective. Hydrophobic treatments, again, will begin to oxidize between 300 and 600 degrees, and it's kind of a function of time and temperature. the longer that it's exposed to these temperatures and the hotter these temperatures are, will determine the rate of the deterioration in the hydrophobic treatment and how it will oxidize off. Once this has happened, your hydrophobic defense against CUI has been lost, and other attributes such as corrosion inhibitors like XOX, jacketing systems, etc., become more important factors to a CUI strategy. Breaches in the jacketing system. Jacketing systems are usually your first line to keep water out of the system, and when there's a breach in those, that's a breach in your first line of defense against CUI. Choosing the right insulations for the applications and conditions is important. A low compressive strength insulation that's installed in an area that could be susceptible to physical damage could eventually render the jacketing system less effective if that jacketing system's damaged. It's kind of depicted in the middle picture here. Having a right insulation under the jacketing can be important to keep the jacketing system intact. The insulation's chemistry is very important as well. Many times the insulation is being installed directly onto the pipe, and how these substances in the chemistry of the insulations react with the chemistry in the piping could be a factor and has less to do with hydrophobicity at all. So jacketing and sealing. Like I said, one of the first lines against the CUI is an effective jacketing system, and keeping water out of the system could starve the system of one of the ingredients, which is water, for corrosion to occur. Typically, in industrial situations, these are usually used are aluminum, galvanized, and stainless steel types of jacketing. Silicone sealants are many times used to seal the joints, especially the circumferential joints, and then the jacketing secured to the insulation with a stainless steel banding on the outside. Other considerations to protect against CUI, as we've been talking about, there are several things to consider when combating CUI. Corrosion inhibitors are an excellent tool to have, especially in hot surface applications when the hydrophobic treatments have oxidized off. Consider using insulations that have corrosion inhibitors as a line of defense against CUI, because once the hydrophobes are gone, you still have a line of defense chemically to inhibit corrosion. I've also been asked on more than one occasion, how long will an insulation system last? And my answer always is, as long as you maintain it. Maintenance is a very important factor for a CUI strategy. If you think of it, if you buy a house and do absolutely nothing to it and don't maintain it, over time it will succumb to the elements. Insulation systems are no different. Developing and executing an effective maintenance program is critical to the longevity and effectiveness of your insulation system and your CUI strategy. Periodic inspections, identifying weaknesses, and fixing those problems are all part of the strategy that need to be employed. Also, surface coatings, pipe coatings. Pipe coatings are sometimes the last line of defense on a pipe against CUI. Proper coatings can be the final barrier that you need to inhibit corrosion and starve it of the elements needed for corrosion to occur. And for additional resources, JM has many technical resources to provide you on this topic and many more. We have a wealth of information, and I'll let Kim expand on that and tell you what we have to offer.
Thanks, Matt. So first and foremost, we're actually going to be hosting our 4th annual Industrial Master's Course this May 14th and 15th in League City, Texas. Now, this is a really unique opportunity. It's a completely free 2-day educational course for industrial engineers and facility operators. And we'll be teaming up with 7 other businesses and manufacturers in the industrial industry to talk about designing, installing, and maintaining effective insulation systems. And our hosts are going to discuss the latest research results, new technology, and nuanced details that can help you design, install, and maintain more effective insulation systems. You should be receiving a chat right now that has a link from Dana Martin with the details for registering for the master's course. Now, the course is limited to 100 people, and we do that to create an environment that fosters engaged dialogue and questions. So you want to sign up quickly to reserve your seat if this is something you're interested in participating in. Now, in addition to the master's course, we maintain all of our information on resources in an online portal called The Source. And this is where you'll have free access to our recorded webinars, our blogs, product documents and specifications, training, and tools. Regarding our blog, we both write and curate content so that we're not only relying on our own expertise here at JM, but we also find information from technical experts throughout the industry. And our blog topics hit on targeted technical information, the latest news in the industry, and even scientific details that can be critical to successful installation system design and operation. Now, we do strive to make this content as rich and relevant as possible so that it can better serve you in the information that you need. There's also a full library of technical documentation on the source, and this includes technical bulletins, white papers, product application guides. Now, if you're looking for information really detailed and specific, this is a great resource, and we strongly encourage you to browse this section if you're looking for detailed information about our products or leading industry issues. In the tools section, you'll find tools like NAMA's 3E+, and that's an online tool that can help you figure out the thickness of insulation you need to specify. And what's unique about this version is that it actually tells you what thickness of JM insulation. So if you download it specifically from the JM site, you'll get thicknesses for JM insulation. If you download it from NAMA's website, you'll get insulation thickness in general. We also have our Smart Binder app, and this gives you fast access to our data sheets and technical documentation right there on your phone. And there's other tools in there that you might find helpful and resourceful for you. Dana should also be sending you a link here shortly in the chat about the source. And you can also find it online on the industrial page on the JM website. There's two ways to access it. First, using the links on the left side of the page. You'll be taken directly to the webinar, blog, or resources tab. Or you can go to the source via the menu on the right side of the page. There's actually a link labeled the source, and that's going to take you directly to the source homepage. As I said earlier, we did record today's webinar, and a recording will be posted on the source in the next couple of days. And when it's live, we'll send you an email with a direct link for access. So if you missed any part of today's presentation, you want to view the webinar a second time, or maybe even feel like this content could be relevant to a colleague, you can access it on demand online here in the next week or so. For anybody who attended today, you will receive a certificate of completion after the webinar, and that can be submitted for professional development hours, and that will be sent to you via email and should be in your inbox by the end of the day on Friday. So with that, we're going to get into some of the questions. The first question we have, I'll go ahead and hand this one to you, Matt, and that is, do you also sell the jacketing?
JM does not sell jacketing to this date. We do not have a jacketing system, but we are aware that it is part of an insulation system and it is needed out there, but we do not manufacture jacketing at this time, metal jacketing.
Okay, to that point, there is a webinar online we did with a metal jacketing company, so if you have any questions about metal jacketing, you could certainly look on the source and find the webinar with ITW, and it should have some information in there if you're looking for more information. The next one, again, is for you, Matt, and that is, does getting insulation with XOX corrosion inhibitor cost extra?
No, it's an integral product, and it's included in our products that we sell, so there is not an added cost to it. And our perlite and our Thermo 1200 calcium silicate has a corrosion inhibitor in all of it that we make. But no, it is not cost extra to have.
Okay. The next question is, does mineral wool come with the XOX corrosion inhibitor, or are there plans to manufacture it with the XOX corrosion inhibitor?
At this time, the only two products that we manufacture with the corrosion inhibitor are our Sproul 1200 perlite and our calcium silicate Thermo 1200. At this time, we do not offer it in the mineral 1200.
All right, thank you. Marybeth, the next question is for you, and that is, why do cyclical conditions increase the potential or probability of corrosion?
So, I mean, even if your normal temperature operating range is outside of what would be considered the severe CUI range, bringing your process up and down will take you likely through that temperature range that is specifically, bad for CUI. So even if, it's not something that you would consider, your process temperature, the possibility still exists during those cyclical up-down periods.
Okay, the next question, thank you. And the next question is this one is for you, Matt, and that is XOX a new part of your calcium silicate, or has it been there from the start?
We introduced XOX in 2002, and it's been included in our Thermo 12 Gold since then, which is a legacy product, and our Thermo 1200, which is our water-repellent calcium silicate that we launched early last year at the end of 2017. But it has been part of our calcium silicate since 2002.
All right, thank you. Marybeth, the next question is for you, and that is what temperature limit do you consider the upper limit for CUI?
So I think in this presentation, we say that the kind of severe range is at 100 to 350 degrees Fahrenheit range. That's not saying that you wouldn't experience CUI at any other temperature ranges. It's just that between that range is where you have the option, or it's likely that you could have liquid water, and then liquid water present is always going to kind of accelerate the risk for CUI.
Excellent, thank you. The next question we have is, what options are available to mitigate CUI on a pipe when the water is not external to the insulation? For example, pipes carrying water of 40 to 50 degrees located in utility tunnels with a pipe insulated to prevent heat transfer of heat to the water. So it sounds like this is a chilled water application. What might we recommend for that? What options are available to mitigate CUI on the pipe when the water is not external to the insulation? So for example, if you have a system carrying water that's 40 to 50 degrees located in utility tunnels and the pipe's actually insulated to prevent heat transfer of heat to the water inside the pipe, what type of insulations would we recommend that could mitigate CUI? This sounds a lot like a district energy application that might be useful for, Insulthin might work that well in that case, and certainly a jacketed system would be important.
Yeah, and if you're more concerned about corrosion inside of the pipe, not on the outside of the pipe, I think that there's a lot of I guess, CUI, or not, it wouldn't be CUI at that point, it would just be pipe corrosion, and there's a lot of other inhibitors or kind of treatments that can be used to mitigate that as well.
Excellent. We can actually follow up on that one privately if you have more questions. Certainly submit that in the survey at the end. Okay, cool. The next question is, what is the maximum thickness recommended for inhibitors in the design according to life expectancy? So Marybeth, can you weigh in one more time on how the corrosion inhibitors work and their relation or lack thereof to the thickness of insulation?
So the thickness of the insulation really isn't going to have any impact on the corrosion inhibiting properties of the insulation. I mean, it's a part of the material itself, so I wouldn't say that it should have any impact on longevity. You're still going to have the same content of silicate ions and high pH buffering components available at the pipe surface because they do leach slowly over time, and you're going to see more of it coming out at the inside of the insulation, I would say, so not necessarily relevant to the thickness.
Excellent, thank you. This next question, I'll offer it to both of you guys, and you can let me know what you come across. Do you see insulation installed in cells? So if a jacket or vapor retarder fails in one location, water doesn't spread as far. Matt, is that something you've seen in the field?
I've seen that in the field in the past, industrially and in commercial applications too. The use of vapor dams in insulation systems could isolate and localize any kind of issues that you would have and keep it from spreading.
Okay. Marybeth, do you have anything to add to that?
No, I don't think so.
Okay. The next question is for you, and is that, do we have any testing on the effectiveness of the XOX corrosion inhibitor when compared to other corrosion inhibitors that are on the market?
So I've not seen any other insulation-based corrosion inhibitors to compare it to. So I can't really answer that question, but I guess if they have some more information on corrosion inhibitors used in insulations, if they could pass that on, we would definitely take a look at it.
All right. The next one is also for you. This is an interesting question, and it is, does the insulation system require moisture or water absorption to release the corrosion inhibitor into action? If so, how does water absorption affect the thermal property of the inhibited products?
So yes, it does require water to activate the corrosion inhibiting properties. So we would never recommend water to be present in the system. From a thermal standpoint, we don't test wet insulation, so I can't comment on how that affects the thermal performance. But once the insulation is dried, I wouldn't expect there to be any negative impact on the thermal performance of the insulation. In the extended testing that we did, the 6-month kind of severe real-world testing that we performed, we didn't see any thermal shift in the performance of the material after it was wetted. That being said, again, I would not recommend maintaining a system with water in your insulation.
All right, our next question is also for you, Marybeth, and that is, if magnetite formation under the insulation is incomplete, won't the steel without magnetite preferentially corrode due to the cathodic nature of this oxide, especially if the anode-cathode ratio becomes unfavorable?
Yeah, I mean, the protectiveness of the magnetite layer really is going to be dependent on the quality of the formation of the magnetite. With the testing that we found, the magnetite layer that we saw on the pipe with the Thermo 1200 and the spool was a very solid layer that did not have a lot of gaps in it whatsoever, and that would be why it would have the effect of impeding further corrosion. So the quality of the formation of that magnetite layer definitely will impact the corrosion inhibition or additional corrosion inhibition of the system.
Great, thank you. The next question I'm going to pose again to you, Marybeth. We've got you on the hot seat. So, with the temperature being one of the required factors for corrosion, are phase change materials inadequate at absorbing enough heat to bring a pipe surface out of the danger corrosion temperature zone?
So you're talking about phase change materials on the pipe surface, so like a coating?
It didn't specify. We could actually follow up with this person privately if you think that might be to get more details.
I guess I'm not really understanding the question, so.
Okay, that's all right. Do we have any research on tests that are relevant to stainless steel pipes or other CRA?
So there's actually a lot of standard corrosion test methods with regard to ASTM that are for stainless steel pipe. So I would reference that for how performance in stainless steel environments. I think that the ASTM standards 665 is exclusively to stainless steel, along with the 795 test as well. So those are both standard practice ASTM corrosion tests. And then I think both of those do also are requirements and material specifications for the mineral wool, the perlite, and the calcil as well.
Okay. Here's an R&D question, and that is, inspecting and detecting CUI is still a large problem in the industry. Is there any development of a smart insulation that could incorporate a detection system when steel corrosion occurs?
So not something that we're working on now, but, give us time.
All right, and then the last question, I'm not sure I'm reading this properly, but it may make more sense to you, and that is, what is the % loading of the XOX corrosion inhibitor in Thermo 1200?
Yeah, I guess I wouldn't really know how to quantify it from a % loading, because it's just a part of the material chemistry, so 100%, I don't know. You're going to have some percentage of leachable components that come out under various conditions. but the material itself contains, you know, all of the ions that we talk about. So I would say that it's throughout the entire material.
All right, cool. And we have one final question, and I think the answer is going to be it varies, but that is, what is the amount of chlorides in hydrophobic versus hydrophilic insulation materials?
Yeah, I mean, it varies. So the material properties of each insulation are different, and that's independent of hydrophobicity. So in calcil and perlite, they're very, very low. In mineral wool, they're a little bit higher. So yeah, I mean, again, and that's something that's going to be probably a part of the material specification. The 871 test that we kind of alluded to for the silicate ion testing also does a chloride and fluoride analysis. So you could probably check with the material specification to see what if there are limitations that exist for that test, or if it's somewhere else in the standard.
Excellent. Well, Matt, Marybeth, thank you both very much for your time today, and thank you everybody who attended. We hope you found this information useful and relevant, and if you have any questions, please don't hesitate to reach out to us directly or via the survey that's going to pop up on your screen directly after the webinar. We'd love to have your feedback and certainly be happy to reach out to you personally. So otherwise, take care and enjoy the rest of your week.